So my name is Rob Homer. I'm a product manager here at Exemplar. I'm going to cover a topic that is quite near and dear to my heart, which is sector coupling in the hydrogen economy. I've done a lot of work on co-optimizing models, and we're going to show at the end of this presentation an example of the co-optimization of the entire North American gas system, along with New England ISO, and some results that you can see coming out of a model that complex and things that you wouldn't be able to see otherwise. Before I start, I do want to actually read a quote here from the FERC Commissioner, Mark Christie. The combination of rapidly increasing electricity demand driven by hyperscale customers such as data centers, paired with the alarming rate of baseload generation retirements and lack of new dispatchable generation is not sustainable and must be addressed. So this was a quote that he put out, I think maybe 2 weeks ago, and it really is resonant of the existing situation that we've got here in the States, in North America, in which we continually see the ramping of a lot of load and the decommissioning of a lot of spinning assets. So I'm going to cover just a little bit about how we got here, some various examples of electrification and hydrogen projects that we've done with Plexos, and then the output of co-optimizing the ISO New England system. So how did we get here? So I know that luckily now I've started to see more people that are younger than me in the industry and around here, and so maybe not everybody is completely familiar with all the different ways and how we ended up in a situation in a complex market like we have today. So back in the 90s, everything was pretty much spinning assets. We're all fuel-based, carbon-producing assets. Outside of hydro, which gets zero credit for being a low carbon emissions generating asset, but generally speaking, this was the existence, and everything was basically dispatchable. And then really what you started to see is the emergence of renewable generation, in particular in the MISO region, where there was substantial amounts of wind power, wind generation, and they really overbuilt in the Mid-American region, in MISO area, to the point where they were basically curtailing a substantial amount of the renewable generation. Ultimately, due to the price pressure, you started to see a lot of coal retirements just due to the aging infrastructure, as well as pricing. Those assets started to get priced out of the market. Ultimately, this leads to a push towards more electrification, so movement away from traditional energy sources, from direct heating or direct consumption at the location. So there's more push around electrification, and I'll talk a little bit about that. I have an example that I'll show, kind of a pseudo Plexos configuration around electrification. Energy storage is now becoming a major component of the conversation. That introduces a substantial amount of complexity on modeling and planning analysis that we're seeing from even short duration to long duration storage to hydrogen storage. And then ultimately, there's real challenges with security of supply and hydrogen as an emerging technology that's coming about. And we'll talk a little bit about that. Won't get too much into the details of it. I've got a webinar that we've done where we really dive into a lot of examples around hydrogen. If you're interested, they're out on our website. So kind of diving into the past and renewable penetration. So as I mentioned here, really what we're talking about is a substantial increase in intermittent resources, a lot of heavy curtailment of that in the region at the time. That was predominantly balanced with hydro. That's how they, in essence, didn't need to bring a lot of battery capacity on. So in order to ensure reliability in the system, hydro was brought on, really balanced the system out. And then they would use peakers, and then started to really use gas-fired. So you started to see ramp up of gas-fired peakers. But at the same time that this was going on, natural gas was extremely expensive in North America. Shale had not come about, and you were starting to see a lot of price volatility in natural gas in the mid-2000s, and shale, like I said, had really not come online. When the shale boom comes out, then you start to see base load come about with natural gas. So at the same time, you start to see a lot of coal retirement. This is ultimately because of aging assets, but obviously emission standards started to lean in on this. These assets were no longer in the money and started to kind of curtail out, or be really kind of mothballed out. So where are we at today, right? So we're seeing a lot of pressure around electrification. From my perspective, electrification really is around two aspects, at least the way I look at it, is one around the transportation sector. So this is going to be around EVs. And the other part of it is that it's electrification of the natural gas industry. So really starting to convert. A lot of states have put in policies such that that no new builds, no new construction of residential and commercial locations can have gas lines pulled into them. They must be electricity only. So a lot of heat pumps are put in. This is not just in the United States, but in other regions, and especially in Europe, UK, Western Europe. There's a lot of pressure to move away from natural gas. And so that electrification process, in fact, in mid-20, I'm gonna say 2016, ICF put out a study in which they basically electrified the entire North American gas system, and showed basically what that cost would be. It was obviously obnoxiously high, but ultimately just as a thought experiment to see exactly what happens if we were to totally electrify the entire North American power system away from natural gas. So, as we're starting to see this high level of renewable assets come online, one of the aspects that obviously people are bringing on is batteries. And so, this short-term battery storage is what most people think of when they talk about energy storage. And batteries actually do account for that kind of in the day. I want to shift my peak from the middle of the day to outside. So I want to charge my batteries in the middle of the day when solar's coming out, and then discharge at night. Using all that arbitrage to capture that in the day. But the reality is that when you start to come out here to the longer duration storage, this is where this is really accounted for. Predominantly in North America, this is methane, right? This is our underground storage, and we have substantial amounts of reliability in our overall energy portfolio and system, given the fact that we have a substantial amount of this underground energy storage. And this is where hydrogen is really the key play, is around this long duration or long-term energy storage. So what does that do for us, right? So some of the things that when we look at different pricing, what you end up with in the bottom right there of the map, that shows where a predominant amount of wind availability is within the US. And this is where we have high frequency of negative pricing. And then the same to be said in Europe. And so what does this mean? Well, you could say, well, it means we need to build transmission, and that's one potential solution. And the other aspect is you potentially could say, well, we need energy storage. We need more quantities of battery and long-term storage. So as we move into the future, what we're starting to see is there's real serious concerns about our security of supply. So, this is a perfect example of Germany, in which they had heavy reliance on natural gas coming from Russia. Russia controlled all of the power and authority. They were able to cut it off, and then Germany basically saw a 3% GDP hit. A lot of people realize, they say, oh, they were fine, there was no issue. I wouldn't say a 3% GDP hit is no problem for Germany during that time period. So now, obviously, with tariffs coming in, this is also another concern. It's obviously been a topic of conversation over this conference so far, but you can see that, the geopolitical and tariffs, and this certainly can create a lot of disruption, creates a lot of supply concerns across different political boundaries. And the other kind of in the future is the emerging technologies. I throw hydrogen here. This was, a topic that has been discussed quite a lot. I think it's, as you think about the hype curve, it was ramping up pretty heavily up the hype curve last year, maybe 2 years ago. It certainly started to settle down on the hype curve. I think that the actual engineering behind hydrogen is starting to come online. People are really starting to understand the complexities of bringing on hydrogen. Nonetheless, there's still a lot of analysis, there's still a lot of planning and investment that's happening within hydrogen. And the main reason why is, if we back up here, it's because its ability to store energy and its zero carbon emissions. Now, we can get into the blue hydrogen and the green hydrogen. Anybody here want to tell me what white hydrogen is? Anybody know? Anybody here know what white hydrogen? Anybody know the green color, the colors of hydrogen? Blue is based on CCS, and yeah, so white hydrogen is actually naturally occurring hydrogen. So it's actually extracted from the ground, just like you would pull methane out. So anyway.
All hydrogen is expensive.
Yeah, that's right. That's right. Exactly. It's all really expensive. And well, I mean, blue is a lot of the projects that are specifically in Europe are around blue hydrogen. It's methane. Blue hydrogen is where you take and you basically crack the molecule. You have hydrogen on one side, you have carbon on the other, and then you CCUS. You carbon capture that carbon and inject it down. There's some interesting projects. There's a company called Modern Hydrogen that's doing a project where they're moving the hydrogen all the way to the back end of the system, closer to the burner tip, and then they basically crack the molecule, and then they capture the carbon as a solid, and then they use that solid to put it in the road. So basically, we're carbon storing in the roads, and this is actually company that's sponsored by Bill Gates. So I actually saw him in PowerGen a few weeks back. It was a really interesting company. Northwest Natural is one of our customers, utility up in gas utility in the Northwest. They are partnering with Modern Hydrogen as one of the first prototypes of that particular solution. So again, talking about the future, new projects, new types of interesting things that are emerging. So why do I talk about all of that, right? So when we talk about Plexos, we talk about Aurora, I mean, we're always looking at the future, and we always got to make sure, I'm a product manager, right? So my job is to make sure that the product can actually do the analysis that we expect it to do, all these emerging technologies and capabilities that come online. So some of the kind of analysis, so one of the studies I did here was really around electrification, and the electrification that impacts a gas utility, right? How do I account for and analyze the conversion of, this could be a gas utility, but it also could be a G&E, and I want to understand the impact to the power generation side as I'm basically deprecating or converting those customers that are currently consuming gas over as an end use. They put a heat pump in, and now I've got power generation's got to keep up with that, right? So this kind of analysis you can do with Plexos. You know, a lot of the big questions are, how much is it going to cost? What's the impact going to be to my rates? You know, is there going to be enough generation capacity? So these types of questions. And so I'm going to move forward. So this is generally, you know, on the bottom right, this is the kind of configuration that we have coming out of Plexos, in which we're modeling, you know, really what would that be a conversion to an electrification on a G&E, typical G&E. And so we have the traditional gas network, which is represented down by that particular section. I've got my power network up here, my carbon capture and accounting for over there. And lastly, I've got what I use as a gas plant that represents, that's why I've got a fulcrum here. It's in essence the mechanism that I use to be able to account for the movement of carbon from one system to another and be able to understand the impacts to my rates, as well as account for the load increase back to my power generation side. So all in one model, I can actually represent the entire electrification and do that analysis so that as potentially as a G&E, as I'm converting, I'm being incentivized, or my state is basically pushing carbon targets to convert customers over to electrification. This is one type of analysis that can be done. So as we move into kind of the hydrogen side of it, right? So as we look at some of the early analysis, so we've had a lot of customers. In fact, Brian, who was in here, presented a little while ago. We've actually done some projects together where we've done some analysis around various aspects of hydrogen. And so here are kind of all the different use cases that represent going around this particular view that we see our customers interested in. So obviously pricing. So we have certain data sets that actually model a full marketplace from hydrogen. So that's really interesting. Understanding the market behavior, what the downstream economies would be for hydrogen, how it potentially gets reblended back into my overall system, you know, potentially how I'm going to operate or size electrolysis facilities through P to X, and then sizing storage, potentially having secondary markets for carbon as I offload carbon into other markets. So some of the regulatory impacts here in North America, 45V, 45Q are two major aspects of the Inflation Reduction Act, which incentivize different aspects to actually investing in hydrogen projects. So just a quick example here of some analysis that we can do with hydrogen. So in the bottom left-hand side, this represents a traditional kind of power system where we've got power generation, batteries. The electrolyzer is up at the top. That represented through a P2X module within Plexos. And then at that point, we've got a downstream hydrogen system. So we've got the topology of a hydrogen system that moves off of that electrolysis facility. And then we have hydrogen storage. So this could be typically long-term storage. It's going to operate more like an underground methane storage. This is typically salt dome storages that sit underground. And then the bottom right-hand side, or bottom left, yeah, bottom right-hand side for you too as well. It is really how you would have a secondary market. So if you wanted to convert it over to ammonia, a lot of the analysis now is determining that moving hydrogen is going to be too expensive without converting it over and modeling it or moving it over as ammonia, and then having a markets to where you're moving and transporting ammonia. All right, so let's talk about this particular study that I did around co-optimizing the North American system and the North American gas system in New England ISO. So, this is kind of what we talk about from Plexos perspective. We have our traditional power system. We have our gas systems, potentially various aspects around biogas, methane. So this is going to be your molecules that you're going to want to analyze. And then we've got various aspects with water, renewables, hydrogen, all within one system. We've got all these aspects within Plexos that you can model. The nice part about it is that when we optimize this, it's one global optimal solution. That's what you have to understand about Plexos. There's no iterating amongst different solutions. It's going to optimize this as one full optimal solution. So it means, what does that mean? That means it's going to simultaneously serve your consumption for your gas, for your hydrogen, for your power, and it's going to meet all of those load requirements, all simultaneously ensuring that I meet those expectations at least cost for that whole system. So our North American model looks like this. So I've got my gas system on the lower left-hand side, power system on the upper right-hand side. The power system includes all known projects in New England as of the time that I built this data set, which was about 18 months ago. And so it had all the known projects, and then on our gas system, it's a little bit of a simplified system that we put together. So we took our gas fundamental, North American fundamental system, we simplified the pipeline network outside of New England, we simplified the storage systems just to make the model optimize a little faster, and then we carved out New England in the upper right-hand side. So this is what it looks like as a bit of an eye chart here, but up in this area, this represents all of the power system, power generating assets. Here's the simplified topology of the pipeline system. The model's going to serve all of the state loads, the province's loads as aggregated demands, and then storages are also aggregated at the state level. And then it has all the detail it possibly can account for within the New England region. So some of the results. So we spent a good bit of time benchmarking this particular model we put together. Obviously, we did a lot of iterating. It's a very complex model for us to go through this process to actually get something that makes sense. And there's a really compelling piece of information, but we didn't get to that. We, in fact, fought it quite a bit. So here's our production. So this represents, the dark blue line represents our standalone North American gas model. Light blue line does that. Dark blue line represents our co-optimized model. So, production's generally the same, a little higher for our co-optimized model, a little bit more stable, not quite as much volatility. Storage inventory. So this is our underground storages operating, same situation. Our light blue line represents our standalone gas model. Our dark blue line represents our co-optimized model. Good, right? Everything's looking good. They're pretty well benchmarked. Great. So let's look at the power side. So here's our generation stack. So up here is my year over year, so the 30-year model. I'm looking at my overall production, and sure enough, it's meeting my demand. Fantastic. Both models are doing a great job of that. Bottom here, we're seeing a little bit of variation between the dispatch by fuel type. So this is aggregated across the entire model run, and we see that the light blue represents our, our standalone ISO New England model, and then the dark blue is our co-optimized model. So, good. All right, fantastic. We're all with us so far. Now we're starting to see some interesting things. Starting to see major price blowouts. So we can see that the co-optimized model generally is a little bit flatter prices earlier on the run, and then we're starting to see a lot more volatility in our power prices. Now here's where it gets really interesting, and here's where we spend a good bit of time trying to understand these results. So this particular view represents the EIA's assumption of power consumption for natural gas in New England, right? This was their general assumptions. This is what a lot of people are using in their models to understand how much gas is going to be consumed in that region for the power sector for the next 30 years. A co-optimized model is the one up above. It's kind of this both blue and orange line. And you can see we're really diverting quite a lot starting out here in 2035. And we spent a good bit of time trying to understand what this meant. And we said, well, it's not right, and this doesn't make any sense. And the reality is that it did make sense, and it was right. So if we look at this, and here's how we know it's right. Here's our load. Here's our power load. It's going up. It's not going down. We have in our model every known possible project for power generation in the system. So what's going to fill that gap, right? We've got this huge gap sitting out here between what we think, what EIA thinks the fuel offtake is going to be for natural gas in the power sector, and here's what our co-optimized model says it's going to be. And this isn't going to, you can't see this information. It wasn't obvious. We had two individual models. We had our gas model and we had our power model, and we're running these two, and we're following, and it all looks fine. But then we look at this and we say, you know, what's going to happen to New England in 2035, right? Well, I mean, we don't have enough. I mean, the model's balanced, but sure enough, there's a huge amount of natural gas, and they've got, in that region, there's huge carbon targets. So if they want to hit the carbon targets in that region, how are they going to do that when we've got natural gas, fuel being consumed just to meet our load? And ultimately, we're going to meet that load at any price. That's what's going to happen. I've talked with many folks up in the ISO New England region. I presented this to FERC 2 weeks ago, and they were like, yeah, we understand this, but we've never been able to actually see it and explain it. So really kind of interesting concept here. And my job isn't to say, what they're doing in New England is right or wrong. What my point about this is that when I brought these two models together, we started to get some really compelling information that's not readily obvious without looking at these systems simultaneously and co-optimizing the system together. So generally speaking, that's kind of the interesting output of this model. So the bottom line here is, this actually came out of a paper it was published by Southwest Power Pool, MISO, PJM, and ISO New England. They sent this actually as the strategies for enhancing gas-electric coordination. So this was published in February of 2024. And it says here, for many grid operators, compounding these challenges is the imminent retirement over the next 5 to 10 years of significant levels of dispatchable thermal generation. This impending shift further accentuates the urgency for coordinated efforts to address the evolving landscape of gas-electric coordination and infrastructure development. So what they're asking us to do is we need to bring these markets closer in alignment. There's so much interdependency between the power and the gas markets in North America that it's just critical that these two systems kind of come into play in much closer balance. So with that, that's my presentation.